We've finally reached the last stage of aerobic metabolism, oxidative phosphorylation. Oxidative phosphorylation is the metabolic process of making ATP using energy obtained from the transfer of electrons in the electron transport chain. We not only entitled the sketch Escape the City in homage to Sketchyland's award-winning dystopian roller coaster ride, but to share its similarities to the electron transport chain in all its glory. Enter the city in the year 2050. Innovations in scientific advancement have led to the creation of giant mice. Unfortunately, a small group of anarchists have been using the giant mice to cause destruction and chaos. The anarchists have also employed killer robots to wreak havoc. Your mission is to escape the city unharmed. We drew the right entrance to look like a mitochondria because that's where oxidative phosphorylation happens. Just a reminder, the mitochondria has an outer and inner membrane. The electron transport chain is embedded in the inner mitochondrial membrane, shown here as the light brown area between the clouds. The intermembrane space is found between the outer and inner membranes. This area is shown in orange above the clouds. Finally, the mitochondrial matrix is found inside the inner membrane. This area is shown in dark brown below the clouds. Before we talk about the electron transport chain, let's recap. We went on pyruvates of the Caribbean, made 2-pyruvate, 2-NADH, and 2-ATP from 1-glucose during glycolysis. Next, we went on pyruvate's dead cove and turned 2-pyruvate into 2-acetyl-CoA and 2-NADH. Then we went on the TCA cycle and got super dizzy, but we made 3 NADH, 1 FADH2, and 1 GTP, or ATP, per acetyl-CoA. So it was worth it. After you add everything up, you'll get 10 NADH, 2 FADH2, and 4 ATP. Recall that we once said that 1 NADH produces 2.5 ATP and 1 FADH2 produces 1.5 ATP. Well, this is where we start to make those conversions. The ETC is the final step of aerobic metabolism, and this is where all that hard work building NADHs and FADH2s finally pays off. We'll spare you the multiplication, but just know that 1 glucose will produce approximately 32 net ATP during aerobic metabolism. That's why the power station is numbered 32. Without further ado, let's go over the components of the electron transport chain. It consists of complex 1, represented by the 1 skyscraper, complex 2, succinate dehydrogenase, represented by building 2 and a worker drying a window with a towel while drinking through a straw, ubiquinone, aka CoQ, represented by that Quality Co advertisement, complex 3, represented by building 3, cytochrome C, represented by a sweet chrome-flying C car, complex 4, cytochrome C oxidase, represented by the old rusty building 4, and complex 5, or ATP synthase, represented by the power station. Whew! Electrons from NADH and FADH2 move along the chain as protons are pumped to the intermembrane space, creating an electrochemical gradient. At the end of the process, ATP synthase harnesses the energy from the gradient to make ATP in a process called chemiosmosis. We drew an O2 tank to help you remember that molecular oxygen serves as the final destination for electrons. Note the water splashing on the tank because oxygen will be converted to water in this process. Before we talk about how electrons move along the chain, you might be wondering how NADH electrons produced during glycolysis enter the mitochondria. The answer is simple. They jump on either the malate aspartate or glycerol phosphate shuttle. The malate aspartate shuttle transports NADH electrons produced by the glycolysis enzyme glyceraldehyde 3-phosphate dehydrogenase into the mitochondria as malate and leaves the mitochondria as aspartate. The malate aspartate shuttle can be remembered by the malfunctioning park shuttle and rider holding an aspartame drink. Another rider is seen holding an NADH energy drink inside the shuttle because the purpose is to transport NADH electrons into the mitochondria. Let's turn your attention to the P-battery-powered glacier gum and NADH energy billboard. Illustrated here is the glycerol phosphate shuttle, which also transports NADH electrons into the mitochondria, but is glycerol 3-phosphate. As you can see in the diagram, we lose 1 NADH to gain 1 FADH2. Since 1 FADH2 makes 1.5 ATP and 1 NADH makes 2.5 ATP, 1 glucose would produce 2 less ATP, giving us a grand total of 30 net ATP via the glycerol phosphate shuttle. You can check out our malate aspartate and glycerol phosphate shuttle sketch to learn more. All right, let's address how electrons move along the chain. FADH2 electrons move from complex 2 to CoQ to complex 3 to cytochrome C to complex 4 and finally to molecular oxygen. The train with the girl holding an FADH2 bar represents the flow of FADH2 electrons. The train starts at building 2, moves through Quality Co in building 3, then passes under the flying chrome C car through building 4, and finally ends near the O2 tank. As electrons are passed along, protons are pumped into the intermembrane space, creating the electrochemical gradient. The plus hats represent protons. In contrast, NADH electrons flow from complex 1 to CoQ to complex 3 to cytochrome C to complex 4 and finally to molecular oxygen. The lightning bolt train with the boy holding an NADH energy drink represents the flow of NADH electrons from NADH. The train starts at building 1, moves through Quality Co in building 3, then passes under the flying chrome C car through building 4, and finally ends near the O2 tank. Just like we discussed earlier, protons, or in this case plus hats, are transported into the intermembrane space. Once all the electrons have passed, protons will travel down their electrochemical gradient to enter the mitochondrial matrix, just like all those cast-aside plus hats falling down the waterfall. We've finally reached the big finale. ATP synthase harnesses the energy from the gradient to make ATP from ADP and PI. Illustrated here is a water wheel powering a robot to add a third P battery, making ATP. Hurrah! Now we just need to do that like 30 times for every molecule of glucose? Oof, I'm exhausted just thinking about it. Okay, let's talk about the toxic agents that disrupt oxidative phosphorylation and ATP synthesis. Electron transport chain inhibitors block ATP synthesis by reducing the electrochemical gradient. Rotenone, antimycin A, carbon monoxide, azide drugs, and cyanide are examples of electron transport chain inhibitors. Rotenone is a naturally occurring pesticide that inhibits complex 1. You can also picture a rotating drone shooting missiles at building 1, which is way cooler and more memorable. Antimycin A is a toxic metabolite produced from Streptomyces bacteria that inhibits complex 3. We've depicted antimycin A as a giant mouse with A-shaped ears trying to destroy building 3. The colorless trash, CN robot shooting cyan lasers, and N3 robot shooting Azure lasers at building 4 will help you remember that carbon monoxide, cyanide, and azide drugs inhibit complex 4. Oligomycin is another toxic metabolite produced from Streptomyces bacteria that blocks ATP production by inhibiting ATP synthase. The giant mouse with an O tail shutting off the power station is oligomycin. And onto the uncoupling agents. The crack in the dam will illustrate how they work. Uncoupling agents disrupt oxidative phosphorylation by increasing the permeability of the inner mitochondrial membrane, allowing protons to prematurely travel down their gradient instead of coupled to ATP synthase. While the plus hats fall down their gradient, they don't fall on the water wheel like they're supposed to, and as a result, the robot remains powerless and unable to make ATP. Uncoupling agents generate heat and increase oxygen consumption. Whenever you think of them, picture this fire and empty O2 tank. 2,4-dinitrophenol, an illegal weight loss supplement, aspirin, and thermogenin, derived from brown fat, are some examples of uncoupling agents. They're represented by the DNP explosive, ASA umpire, and thermite bomb, respectively. Okay, let's wrap up this sketch. Oxidative phosphorylation is a metabolic process of making ATP using energy obtained from electron transport. It takes place in the mitochondria and requires the electron transport chain, which consists of complex 1, complex 2, CoQ, complex 3, cytochrome C, complex 4, and ATP synthase. NADH and FADH2 electrons move along the electron transport chain while protons are transported to the intermembrane space, creating the electrochemical gradient. ATP synthase uses the energy created from protons traveling down their gradient to make ATP. Oxygen accepts electrons after they've passed through the electron transport chain to make water. Rotenone, antimycin A, carbon monoxide, cyanide, and azide drugs block ATP synthesis by preventing the flow of electrons across the electron transport chain. Oligomycin directly inhibits ATP synthase. In contrast, uncoupling agents make the inner mitochondrial membrane more permeable. As a result, they reduce the gradient, reduce ATP synthesis, generate heat, and increase oxygen consumption. 2,4-dinitrophenol, aspirin, and thermogenin are uncoupling agents.